Is the mic good? Okay. Okay, or continue the blocking design. I already explained last time that you can consider that the total sum of that's odd. Is it on? Oh, okay. Okay, so first thing first, sum of square total is the distance of each one of the observation to the central station. No problem, right? And then we can consider that if I consider car 1, car 2, car 3, car 4 are 4 subway stations, then I can calculate each one of the observation, how far away from the subway station based on the car, and come up with the sum of square car, right? And I can also calculate the sum of square using the tire brand. So I can have brand 1, brand 2, brand 3. I can have brand A, brand B, and so I can treat every car, the tire brand A, B, C, D as the subway station, and then I can calculate the subway station total from the brand. But in reality, to calculate the sum of square error, you know that a sum of square error should equal to the total pie chart. Cut off the sum of square for car, sum of square for brand, whatever the leftover. So one way you can look at that is saying that, okay, I see the world through two different frame of reference. So if I break the differences, the total pie, sum of square total, into the sum of square car and sum of square tire brand, whatever the leftover, sum of square total minus the other two is the leftover. But to calculate that, okay, there's another way you can calculate that, is basically say, hey, what is the local commute going to be? But to calculate the local commute, remember, originally, when we did the sum of square, we only consider, my home to the central station and break them into two pieces, right? To the subway station and from the subway station to the central station. But now we're really faking this and say that, there are two different subway stations. One is using the car subway station, and then from the subway station car to the central, or using the tire brand and using the tire brand to the central. So in reality, we're only doing one trip. But if you do this Pythagorean theorem in two different views, like what I explained last time, almost like I have an evil twin, right? One using the car trip, with the other one using the tire brand trip. So if you want to do it individually, okay, then you have to use everything minus the car differences and the brand differences. But then you really treating this like there are two trips. If you have two trips, you have to, for each one of the trip, embedded was one G7 in there. So the central station in this one, central station in this one. But in reality, you only have one observation, B3. You cut it here, you cut it here. In other words, you cut that Pythagorean theorem twice. And that's wrong, right? So the only way you can compensate that back is, hey, You only did it once. So you only have one central station. So you did a central station here, you did a central station here, minus, minus. Then I have to add one central station back in order to balance it. So if you do it this way, this is your local commune, and then you sum them up, you get your local commune or your error term. So this 11.5625 is the true local commune. But you compare that with this, you will have the same number. And so, in other words, is that whenever you're doing this kind of computation, here is a way to double check. One way to figure out what's the total sum of square is just total minus this guy, that's the leftover. Or you can do it individually. But when you do it individually, you need to remember, add one back. If you don't add one back, you're in trouble. And later I will talk about Latin square or Greco-Latin square. Guess what's the Latin square or Greco-Latin square? We'll have three different ways to see the subway station system. One is, I think in Chicago, they have the elevated train and they have the underground train. But no matter what, sometimes just two different systems but will reach the same location. So for every local commune is either I go for the elevated or I go for the subway. But when you do the computation, you need to add one back. And then if you have three different subway systems or three different public systems, say you can take the bus, you can take the elevated, you can take the subway. Now, when you do the computation, you still can consider the total bar pie chart. You will have kind of like subway system 1, subway system 2, public transportation system 1, system 2, system 3. You subtract the 3, whatever left over is your local commune. But if you want to calculate them individually, guess how many you need to add back if you have three different systems? You have to add 2 central stations back in order to balance it. Okay? And I'll show you computationally. This is one way I do cross-check. Okay? How many of you ever take accounting? Yeah. Accounting, they have the similar things. Is a lot of time you can itemize stuff, you can consider central planning, but no matter what, at the end, you have to balance it. The inflow and outflow should be equal. Okay? And I can share with you another example is that I used to work for United Airlines before I study in graduate school. And airplanes, the old days, 747, wide body, cross Pacific, you need to balance the aircraft. So you have to have certain payload at front, certain payload at back. But the center of mass, or the mean value, must inside the wing. And of course, cross Pacific flight, there are a lot of fuel in the fuel tank in the wing. But when you consume all the fuel, the aircraft become lighter. The center of mass starts shifting. But no matter what, you need to keep the center of mass inside the wing. So when we develop some computer program to do that, it's the same things. I have the cargo load from coming in from different source. And then I distribute them or calculate them. One is based on the weight and balance. One is based on the location of the stop. But no matter what, it's the same set of cargo. I just look at them through 2 different view or three different view. And at the end, you just have to balance it. You cannot. So this sounds simple mathematically, but can you see? Okay, just quick show hands. Everybody can visualize why we need to add one central station back, right? Anybody, if you're confused, just wiggle your finger. Okay, here. In the old days, if I don't consider the car, I just have a bunch of local commute, 16, and then, well, let's just say that 16 local commute, and then 4 different treatment. And sum of square total equal to sum of square trend, this brand, and the error term, right? That was our week 1, agree? And then, of course, this is looking down this way. But can I pretend, just ignore this whole thing and say, hey, I'm going to reuse this 16 value, but I'm going to look at the world not this way, but this way. So do I have 4 treatment, car 1, car 2, car 3, 4 blocks? And then I still can do this and calculate the sum of square error, right? But now you're facing the problem is that, okay, in reality, you can have your breakdown this way, you can have the breakdown this way. But how many observations you actually have? 1 set, 2 U's, right? So if you do it this way, would you agree with me that every observation embedded inside there are, you can consider this. I know how to write it down. So I can consider every observation Y or every observation X. Okay? I can say every observation X could be due to the overall average. The overall average, 16 average, never change, right? So I can have a mu. Okay? And then can I have the influence because of different car? So I can have the car influence. Okay? And I can have the brand influence. And of course, right now we consider there's no interaction since this is not factor. So symbol is mu. Okay? Where is my symbol? Oh, here we go. Okay. So every observation is a combination of these 3 different things and the error term. Okay? But when I'm doing my computation, I'm basically said that I'm going to do one computation without a brand. I'm going to do one computation without a car. Okay? And then I'm going to use, right, one is this way, one is this way. And so when I add them up together, okay, you're going to have what? 2 mu, but 1 car and 1 brand. And that's why when you do the computation, the only way you can balance it to get it, the Pythagorean theorem, is you need to add 1 mu back. Is that?
Yeah, that makes
okay.
sense. Yeah.
Okay. So if you done this, okay, now you turn the whole things into the total sum of square into this ANOVA table. But when you have this ANOVA table, remember, total number of degrees of freedom still 16 minus 1 is 15, just like before. And then the brand will take 3 degrees of freedom because I have 4 brand. The car block will take 3 degrees of freedom. So whatever leftover is 15 minus 3 is 9 degrees of freedom. Okay? And what I would like you to start thinking about this sum of square things and this degrees of freedom things. Is you consider there are 2 pi or 2 pizza here. And whenever in this class, or most of the class I'm in, I always like to talk about greedy algorithm. What is greedy algorithm is, for example, say exam is tomorrow. I'm just making that up, okay? And if exam is tomorrow, you only have a few hours to study, what will be the first things you do? You probably will go for the most likely problem and do the exercise there. Would you agree? So greedy algorithm is saying that, okay, there are sum of square, there are sum of square. Where should I do my job first? So, for example, see here, I'm only using 3 degrees of freedom, but a car will use 38.69 degrees of sum of square. That's the things I'm usually interested in. So, in other words, is that when we're sharing a pizza or sharing something, you always want to say, hey, I want to go first. And everybody will say, why you go first? I want to explain first. Who got a priority to explain first? The one who can use up a lot of sum of square. That's why it's called greedy. It's kind of like, here is a big gulp of Coke. Everybody say, oh, 5 o'clock, I want some Coke. And then who can drink first? The one who can say that, let me try. One sucks, say half cup. He is the one who can take out as much of variation, as much of sum of square. He should go first. Okay? So later on, this is kind of like the accounting or the things we always have in mind about the economics of design of experiment. Always use few degrees of freedom, but take away as much sum of square as possible. That usually is the things we would like to get. Okay? And what will be the terrible things to get? Few degrees of, use up a lot of degrees of freedom, but explain very, very little. Okay? So, can you guys see now ANOVA table got a little bit of kind of intelligence economics in there? Who is the smartest person? Use few sentences, but explain tons of stuff. You don't want to have someone yada, yada, yada for hours, but never get to the point. Okay? So this is the kind of intelligence you need to demonstrate. Okay? And then, of course, after that, you divide it by the degrees of freedom, you get your MS term. And then you get your MS term, or the MS term divided by the error term, you get your F-test done and your F-statistics, just like before. Okay? And here is the algebraic way to do that. Basically said, hey, how can I get my sum of square total partition into the sum of square brand is the total of each one of the brand divided by 4 minus the overall average, and then you get this term. And or you can calculate it using for car. So here is basically showing what I did in Excel. One calculated downward, one calculated sideways. Downward for brand, sideways for car. That's how you get your number algebraically. And then, of course, you need to compare that with your F statistics. And F statistics, the yardsticks you will use is, okay, the F statistics here is 10.2 minus 1.3. The brand is the brand significant, 10.2 over 1.3. The F value is 7.8. And then you compare that 7.8 with your yardstick value. So let me do that to refresh your memory. Excel. Okay, so we can do it 2 different ways. One is to figure out a p-value. So we just do F inverse. No, we'll do F distribution first. F distribution, I will have my 7.8. And then that's my ratio. And the degrees of freedom upstairs is 3. Downstairs is 9. And I'm using, I need to say it's using cumulative, so using 1. And this is the value, and then I'm looking at the other end. So the other end of this, so the p-value is 0.07. So there's, can you see it? Oh, you want to see how I get that? Okay. Everybody know where the 7.8 coming from, right? And the 3 degree, and the 9 degree, and cumulative. But that, I give my F distribution from 0 to how far 7.8 is. But I'm interested in the leftover. The leftover is 1 minus that is this. So, young man in the back, your turn. Okay, yeah. The one was, okay, so 0.07, significant or not significant for my brain? Significant or not significant if alpha is 0.05?
Since it's lesser than 0.05, it's significant.
Yeah, or you can think about it as what? Here, 7.8 for 3 degree, 9 degree F distribution, 7.8 is really big or not very big? 7.8 is extremely big because whatever the leftover is what? Only 0.07. Or you can consider that how big is if I use this. Okay? Is 99.2867% of time, okay, you're not going to be that big. The only way you can be that big to be 7.8, okay, is beyond 99.2876 time percentage. Remember, we have a histogram. The further we're going outward to the right, the bigger the number, the percentage is getting higher and higher, right? Sooner or later, almost 0.99999, right? So how far out is 7.8? It's actually pretty far out. 0.99. That's p-value. Okay? And this is part of the reason I torture you with those histogram, because if you can see the histogram, the CDF, the PDF, you should know what this means. And the other way you can calculate this is just doing F inversed, okay? And no, I cannot do F inverse. I have to do, I can do F inverse. And then just 0.95, because I'm only interested in 3.9. Okay? And then here is your yardsticks. Your yardstick says that if your F statistics, okay, is reaching 3.86258, you're 95%, reaching 95% of the chance. So what do we get? 10.8. 10.8 is bigger or smaller than 3.86? Way, way, way bigger. So you know that it's not going to be 95%. It's going to be, 99 something. So this is your F critical value. Okay? Next. Now let's try a different problem. This problem actually is very popular right now. Is a lot of time COVID-19 they develop vaccine, so they will hire a bunch of human subjects, and then let's just say that this one I think is weight loss program or some medicine. Before the test, before I give them the treatment, before the test, here is the value. And then after we give them the vaccine, and we're gonna check them again, right? Actually, right now, how many of you have the vaccine shot? Yay, good. And you know, when they give me the CDC card the first time, I just one look, I realized that, man, I'm gonna have more than 6 shots. You know how I figured that out? I look at the blanks for the stamp. Is there only one, or they have several rows for you to, for them to put down number? And I said that, you know, CDC never say we're gonna have more shots, but I just look at that as, oh, this thing's gonna be forever, okay? And so you could have this in a similar way. Time 0, check, check, check. What's your, you know, I don't know, some COVID test score. And then you can test them again, and then test them again. So I'm only test them twice, okay, before and after. So if you look at this before and after, can you consider every human subject as a block? Done it before, done it after. Can I calculate the before average, after average? I can calculate every subject on average. And then if I do that, can I figure out the sum of square total of this 14 value? This 14 value overall average. And then everybody minus that. Okay. First, you figure out the average. The sum of square total, okay, is the everybody minus, okay, the overall average, and then you get that, okay? And there's another way you can get that, okay? Actually is it's doing this. Let me do that just for fun. Okay, you just calculate like what I did before. Sums, no, I just do standard deviation of all 14 observation, and then I'll square it, and I'll square them. Okay. And then that's the distance, and then all of them needs to, oops. Strange. Yeah, let me redo it. Is 14, so it's 14 minus 1 times standard deviation of this value square. See, I'll get exactly the same value. And what I'm doing here is telling you that one way to think about sum of square or mean square, you can consider that there's variance at different level. Okay? And similarly, now I can calculate the subject before and after. So every one of them minus the before and after. And here, can anybody explain to me why the before and after value is exactly the same? See here? Why before and after? Before is subject 4, before is 4.59, and after is 4.59. This only happened in this case. Why is that?
Because the treatment didn't work?
No. Everything's the same. See here? Could be high, could be low. Here, I am subject number 5. Okay? before and after treatment, my value is 100. So if before my value is 95, what will be the value after? 105, right? Otherwise, I won't be 100. And if my value average is 228, and before is 226, after must be 230. And then, so everything, when you square them, there will be one positive square, one negative square, but they will be exactly the same. And when you sum them up together, you get your sum of square subject. And then, of course, you have the treatment before and treatment after. And the treatment before and treatment after, same things. On average, everybody gained 10 pounds before the treatment. Then that means what? I'm 10 above average before the treatment, then must be 10 below after the treatment. Otherwise, you're not going to get this. And then, so when you have all of them together, okay, you can figure out your sum of square error term by doing the same things. Sum of square total minus square sum of square treatment minus sum of square subject. Or you can do that individually. But when you do that individually, have you noticed we still need to add the overall average back once? Okay? And this is the kind of like, how we use that for COVID-19 type of epidemiology study. And when you turn them back in, you have your sum of square total, sum of square subject, sum of square treatment. And this time, total degrees of freedom, 613, no problem. Agree? And 7 subject means 7 block. 7 minus 1, you get 6 degrees of freedom. Treatment, you only have 1 treatment. Well, actually, you have 2 treatment before and after. So you have 2 minus 1, you have 1 degrees of freedom. So leftover is 6 degrees of freedom. Okay? And in order to calculate your F-test, you need to figure out your mean value and mean square. So mean square divided by 5.95, it's 58. Divided by, and this 800 something divided by this is 145. Okay? So based on this, you can find your critical F value, you can find your P value, and here's your P value and your F critical value. This time, I'm just give you the table, you figure that out in Excel yourself. Okay? You should be able to find those two values. But just one look, okay? Whenever I see here, you see a tiny, tiny bit of error term. 6 degrees of freedom, use F 35. To shear 35. And now you see the treatment. One treatment is 1 degrees of freedom for treatment is 800 something. Without even looking any table, just one look, I'll say, yeah, that's going to be very, very significant. Okay? Okay, now I'm going to talk about something you need to learn. Is sometimes, when we run experiment, you finish the experiment and you realize, man, 16 value, I have 1 value missing. I lost 1 of my data point. Okay? So how are you going to get that data point? It's already done. You don't have money, you don't have time. Make up a value and put it in there. Right? Then, well, that's actually what we're doing here. But what will be the most reasonable value to cook and put it in there? Huh? The average? Good point. But it's the average of what? The average of the central station location? And for the car and brand, how many different averages I can have? 3, right? I can use the 16 average, which is the central station location. I can have the brand, each car brand, or which car brand you're in, or I can use what? I can use the tire, the car or the tire to be that. So there are 3 different average. All 3 play a role. Which one should I use? So the tricks here is doing the following, okay? You basically said that first, okay, here is my total number of observation, okay? This car 3, tire C is missing, right? So according to what you just tell me, how to figure that value. One possibility is using this divided by 16, divided by 15, put that value in. Or I can do it this way, put this 3 value, 12, 12, 9. 12, 12, 9 is 33. And said that 33 divided by 3 is 11. So I put 11 here. Or I can say that using the car, this car on average is 13, 13, 11, that's 37. So I can use 12.333 to put it in. So there are 3 different possibilities I can use. And the question becomes, which one should I use? Which one should I use is, here, let me give you one example. During the summer, did you guys take a road trip, driving to somewhere? And I hope you're the driver. And then say your friend, one sitting right next to you as your co-pilot, one sitting behind using the GPS is your backseat driver. And both try to give you advice. Goes this way, goes that way, goes this way, goes that way. Who you trust most? The one right next to you or the one sitting in the back? Huh? What? No, both are using some GPS. Like my phone got one GPS, and there's a Google map, there's another, there are several versions. And I know my GPS sometimes give me the worst directions. So usually what will be the answer is whoever can give you the least errors, right? You trust the one give you least error. So what is the least error coming from? So in other words, is that, say, your backseat driver 1, your backseat driver 2. You give me 20 points of error. You give me 40 points of error. I should trust you more, right? So how am I going to weigh this whole thing is I'll put 40 on you, 20 on him. You follow me? That way, it's kind of like, oh, why you gain his weight? Because you make less error. Okay? And actually, this view, just like when I talk about why YouTube, only updates certain pieces, this is all some computational intelligence that people develop over the years. And here is the way how we can figure that out. Is, okay, here, let me open up. First, you will have every observation, okay? And in order to make the computation easier, we just find why I'm using 13. Here, which values show up the most? 13. And then I just say that, oh, I will just use 13, make up a number. Say 13 is my frame of reference. So if every value minus 13, then you will have some overestimate, some underestimates, and then a bunch of zero. Okay? And that's the number one reason we use 13, because that way, how many computation I need? Because I get rid of 13. 13 will turn into 0. 17 is 4 above 13. 14 is 1 above. 12 is 1 below. So now you can consider that I have some value above, some value below 13. And then you basically said that those things, will constitute my sum of square error. Due to, if I call this value missing, y, is everything's, okay, minus plus is y squared. Okay, this is overall. So I have 16 value here, square, including a y square. And then I can have the Brand error. So add a Brand error back 4 times, and a car error back 4 times. And then, of course, remember our computation in sum of square error. Overall, minus the Brand, minus the car, we need to add 1 back. So we add 1 back. And once you do that, okay, this whole equations can be considered as something we would like to minimize. Why? Because sum of square error should be as small as possible. In other words, is that if y estimate is wrong due to the local, due to the Brand estimate, due to the computation to the car estimate, you can cause a mistake. He can cause a mistake. I trust nobody. I would like the mistakes as small as possible with different source. Local commute, the Brand commute, the car sum, and this sum. So when you have this whole things together is a polynomial of, usually just quadratic, okay? In this class, we're not going to go beyond quadratics. And here, this is a y square. So here's y squared, so the derivative of y is what? 2y, right? And here is y minus 6 squared. The derivative should be 2 times y minus 6 and divided by 4. And I have a negative outside. And here is y minus 2 squared, so it's 2 minus y, 4, negative outside. And finally, 2y minus 12, 16. So now, this whole equations become 9y equal to negative 20. So y is negative 2.2. So here, the yellow points should put down y equal to 2.2. But if this estimation, yellow point, y is 2.2, that's how I figure out all the contribution, right? But remember, if here the computation A1 is 4, original is 17. Here I got a 2.2, then that means that originally here, what will be the estimation? 13 plus, minus 2.2. Okay, so if I do that, okay, at the end, oops. We can find the 13 minus 2.2 is what? 10.8, yeah. So If the missing value for the yellow points, 2.2, plus 13, you get 10.8. So the best estimate, the least square estimate of your missing value is 10.8. Okay. And after we done that, I put the 10.8 back. Okay? This 10.8 is not a real value, right? It's the value, it's a missing value we fake. And once you do that, you put a 10.8 back, you can still pretend that's not a fake value, that's a real value. Can you calculate sum of square total, sum of square brain, sum of square everything's, and then you figure out sum of square error term? Can you do that? Okay? And that's your 11.22. And one thing I can force you to play with is in the homework or in the exam is what? I said, hey, don't use 10.8. Use something else. 5.5, 20.2, whatever other value you put it in, your sum of square error will increase or decrease. Will increase. Why? Because that's not the error term was the least effort from different directions. Okay? So, can you guys see that sum of square really is kind of like, philosophically, it's like human in life, right? We're walking forward and there are ropes from family, from colleagues, from career, from society. They're all pulling you in every possible directions. How you maintain equilibrium is you let all the sum of all the pulling force sum together at the location you are should equal to what? Nothing, right? Because if one side is more than the other, you will be what? Going that way even more. So yeah, so sum of square, if you think hard, okay, reflects certain reality of life, right? That's supposed to be a joke. Nobody laughed. Yeah.
Could you go back a little bit? You go kind of fast through all of that, and when we get to that missing value.
Oh, you mean this part?
Yeah. So
Okay.
I see that, and I see like the final answer. I don't see how the two, like how you pulled the information from what's going on here.
Okay.
So get to that.
Okay, here. First thing first. This is original 15 value with one missing value. And then I said that I need to do some estimation. And then one way you can do that is doing this, okay, using mode function, and said that, okay, majority of this, what's the value? Is 13. And then say that let everybody minus 13. In this part, only one reason, convenience. Because if I use 13, I will have a bunch of 0. And if I have a bunch of 0, when I do that partial or derivative, life will be easier, less terms to calculate. So now, you will have new 15 value with a bunch of 0. Agree? Okay, so once you have a bunch of 0 and that done, the rest is just this part. Okay?
Is that part math? Like with
Yeah. Here, the best way you can look at this is 15 value, including the y, should be involved there. So far, so good?
Yes.
And then here I will have the phi car brand, the tire brand, sum of square. Here, go back for one. Yeah, actually right here. You see the phi, -3, -6, -8. That is this part. Okay, look at here. Down below here, A, B, C, D, I have the average, right? That is the subway station based on the, see the phi, -3, -6, -8. That is where phi, 3, negative 3 is 6. But remember, the negative 6 only got 3 value. Y is not involved, so I need to add a y in the negative 3. So y plus negative 3 become y minus 6 squared. And then finally, negative a squared. And then those sum of square divided by 4. So far, so good? 5, negative 3, negative 6, plus 8, or y. And then 8. So far, so good? And then, of course, on this side, I'll play the same tricks. I have a 4, negative 1, negative 2, plus the missing value y. So it's 2, negative 2 plus the missing value y squared. And then finally, negative 13 squared. That will be my car sum of square. So far, so good? And then finally, okay, I have the total 12. Okay, but with one missing value y. So it's negative 12 plus y, but divided not by 4, but by 16. Remember, we need to add one more back. Right? So now, observation minus the car sum of square average minus the brand average minus car average, add the one more back. That is the constitution of my sum of square error term.
Okay, I followed really, really well until where did the 12 come from?
What?
Where did the 12 come from in that last little part?
Oh, 86 divided by, here. All those values added up together is negative 12.
Okay, got it.
Okay? Because that's still the overall average, overall, right? Except this overall is 12, negative 12, but need to add one more, the y, the missing value y.
Got it.
Okay. Okay, everybody on the same page now? Okay, and homework probably will be your 5 by 5, but still one missing value and doing the same tricks. Okay? Am I good?
You got 10 minutes.
Okay. Okay. Now let's talk about Latin square. Latin square is the following, okay? Latin square, let me talk about what I want first, okay? Originally, I have the 16 value, right? And I said that, oh, I have the brand sum of square, I have the car sum of square. But think about it this way, okay? If I have 4 different tire, A, B, C, D, would you complain that, say we're always doing pickup trucks, and then tire A always using at the front, and tire C always using in the back? Say is a pickup F-250. If your certain tire brand, would you consider this experiment is what? Not fair, right? Why that brand is always mounted in the front? My brand is always mounted in the back. My tear and wear is not under the same conditions. So one way to balance that will be what? Everybody get a chance to mount it in left front, left back, right front, right back. So I have 4 positions I can use. So as such, I can have, position left front, 1, 2, 3, 4. Left front, left rear, right rear. And then I can have 4 different cars. So every tire brand, look at here, will be mounted in every car once. C, 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 C. In every position once. A, B, B, B. D, 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 D. Everybody see that? So if you do that, that means what? You kind of even out every possible opportunity. So if you do that, of course, you can think about this. originally, okay, in your homework 1, 16 observation, 15 degrees of freedom, after 3 treatment, how much left for your error term? 12, right? And then in a blocking design, 3 treatment, and after that, 3 tire brand, and then 3 car. 3, 15 minus 6, I have 9 degrees of freedom left. Now, if I have another one is location, the positions, use up another 3 degrees of freedom. How much left for your error term? 6. So your error term is got consumed more and more by those things you try to explain. And of course, I can add another one, use out another 3 degrees of freedom. If I have another level, it's called gray colliding square. You're basically doing what? You're saying that, hey, I am very stingy, or my boss is very stingy. He's not going to let me run a 16 trial experiment without explaining as much as possible. So he will say, use up 3 degrees of freedom for brain. Use up 3 degrees of freedom for error term, for car. Use up 3 degrees of freedom for position. Let's just say, use up another 3 degrees of freedom for driver. Sooner or later, what will be the problem? You don't have much left for your error term. And then at the end, it's nothing can be explained or tested because there's nothing left for your error term. Then you're in big trouble, right? Later on, I'm going to teach you how to deal with the stingy boss. The way how we do it is we explain everything we want to explain. And then we bubble sort them. There are some sum of square used up really quick. We know those are important ones. We'll keep it. And those doesn't give too much explaining power. We'll say, nah, we'll ignore that. We'll pull them down and fake them as your error term. So your error term is not really from design now. Your error term is from what? Whatever leftover I'm going to use. Okay? So to calculate, 5 minutes? Yeah. Okay. Your fault. No, I'm joking.
So you
No.
want to have error?
Huh?
Error is necessary.
Well, without error, you cannot do your F-test.
So you don't want to minimize error?
Well, so, no. You never minimize your error.
Okay.
And actually, that's a good way to stop me here, is error is necessary evil. You cannot get rid of it, because if you get rid of that, you cannot do your F-test. But at the same time, since it's evil, what we really want to do is always, in a experimental intelligence, is that greedy. Explain what I want to explain. Use up those big sum of square with few degrees of freedom. And then whatever at the end, and saying that, hey, there are some things, useless, cannot explain anything. Then you dump it into the error term. It's almost like this, okay? Anybody get a rotisserie chicken from Food Lions before? Okay, the wings you eat first. The drum you use it for your lunchbox. And the chicken breast for the salad and everything. And sooner or later, there's a tiny bit of neck and the ribs, bones left. Okay? It's no meat, right? But you still can use that for soup base, right? So nothing wasted. The big piece for something more important. The not so important pieces will save it for your error term. That is the take-home message I'm trying to introduce early. Okay? Okay, I think I have to stop here, and I'll give you the homework later.